Power systems. All communication satellites obtain their electric power from solar cells, which convert incident sunlight into electrical energy. So all the satellite will contain this type of solar panel, right? And the solar panel will generate the corresponding certain electric power, and the whole satellite will work with the help of that electric power. But there are certain situations where the satellite may not be rather able to receive the solar ray directly, right? Those are called the eclipse. So what will happen under those conditions? Will the satellite be closed or shut down? The answer is no. For that, some backup system must be there. Okay, that means there must be some kind of battery present in the satellite system. So during those period of time when direct sunlight uh, will not incident on the solar panel, that means solar panel will not be able to generate the sufficient amount of power, backup supply will be there, batteries will be there, and for that particular time period the battery will control, or battery will supply all the power. Obviously the weight of the battery is very high, right? And also it takes some sufficient amount of volume. You cannot have huge amount of battery present in the satellite, because at that situation the launching cost would be very high. So backup power is limited, right? That means, suppose, just for an example, if the solar panel generates, say, suppose 10 kilowatt of power, then you cannot launch a battery supply that will generate that will provide 10 kilowatt of power. It may be 2 kilowatt of power. Battery may provide 2 kilowatt of power. So what will happen to the other part of the system? Moment, for the time being, other than essential parts, all the other parts should be shut down. Okay, so essential parts will be run by the battery backup, and other parts will be shut down for the time being. And once the satellite starts receiving the sun ray, they will be booted up according to the required power. Okay, the radiation falling on the satellite has an intensity of 1.39 kilowatt per meter square in the sky. I am reading out first. The solar cells do not convert all this incident energy into electrical power. Their efficiency is around 20 to 25% at the beginning of life, but falls with time because of aging of the cells and etching of the surface by micrometeor impacts. So as the time passes, the efficiency of those solar panels will actually diminished. Since sufficient power must be available at the end of life of the satellites, that means after several years of the satellite, to supply all the systems on board, about 15% extra area of solar cells is usually provided as an allowance for aging. That means if say 10 kilowatt power is required, then the satellite should provide the uh, say 11.5 or 12 kilowatt of power at the beginning of the life, right? So that due to aging, when the efficiency falls, efficiency is reduced, the amount of power generated by the solar panel will also be reduced, and it will be very close to 10 kilowatt at the end of lifetime, which is sufficient to power up all the systems, right? So that's the idea. A spin stabilized satellite usually has a cylindrical body covered in solar cells that we have said when we have first shown this figure. Because the solar cells are on a cylindrical surface, half of the cells are not illuminated at all, and at the edges of the illumination, like here near this region, edges of the illuminated half, the low angle of incidence results in little electrical power being generated. So obviously, large communication satellites for direct broadcast operation generates up to 6 kilowatt from solar power for this type of satellites. Okay, cylindrical satellites. So that's the problem of this cylindrical structure. In older satellites, they used to be cylindrical in shape, but their power generated by the solar cell were smaller, like up to 6 kilowatt. And at that time, the efficiency of the solar cells were also very poor, right? But there are certain advantages of this particular structure. The structure actually rotates, right? If this one is rotating in the clockwise direction, this part will be rotating in the reverse direction, right? So what happens, uh, because of this fast rotation, the portion of the cells which is in front of the sun will be heated up, right? And the portion which is away from the sun in the opposite direction, it will be cooled down. But since the body is moving at a very fast rate, the change in temperature will not that high, so it will maintain some average temperature. Okay, so amount of aging is actually lower, hmm, compared to the other system, three axis stabilized system. So that is one of the advantage of this particular structure. Okay, now three axis stabilized satellite can make better use of its solar cell area, since the cells can be arranged on flat panels and that can be rotated to maintain normal incidence of the sunlight. Only one third of the total area of solar cell is needed relative to a spinner with some savings in weight. Now, power in excess of 10 kilowatt can be generated with large arrays like this one. To obtain 10 kilowatt from a spinner requires a very large body on which to place the solar cells, which may then exceed the maximum payload dimension of the launch vehicle. Solar cells must be rotated by an electrical motor once per 24 hours to keep the cells in full sunlight. That means the orientation, we can alter the orientation. This causes the cells to heat up, typically 50 degree to 80 degree centigrade, which causes a drop in output voltage. Uh, in the spinner design, the cells cool down when the shadow and run at 20 degree to 30 degree centigrade with somewhat higher efficiency that we have just said in our previous slide. The bombardment of the cells by proton or electrons is also more severe, and a thicker layer of glass may be needed to slow down deterioration of the cells, with a consequence of weight penalty. More the weight, uh, higher will be the launching cost. Mind it, right? So that's the problem with this particular kind of system. We have to provide uh, thicker coating on the solar cells for this particular structure. Now, satellite must carry batteries to power the subsystem during launch and during eclipses. Batteries are usually of the nickel hydrogen type, which do not gas when charging and have good reliability and a long life, and can be safely discharged to 70% of their capacity. You know what? Satellite is peculiar system because you have to think what is going to happen after 10 to 15 years, and based on that you have to design your system, right? Now if there is some problem in the design, then the lifespan of that particular satellite would be reduced, and huge cost involves in with each satellite, right? The launching cost, the maintenance cost, everything is very high. So particularly for geostationary satellite, uh, you cannot afford Uh, you cannot just throw out a satellite within 6 to 7 years. You have to maximize the lifespan, right? And for that, you have to take necessary action before launching. That's the problem. You cannot reload it. If you found some problem in general system with arts based system, you can easily modify those system. But for satellite, once it is launched, you have you cannot have anything to repair. For as per repair is concerned, as per fuel is concerned, you cannot touch it, right? So that's the big problem with the satellite system. Once it is launched, it is gone forever, right? You cannot add anything to that particular satellite, right? So that's the problem. A power conditioning unit controls the charging current and dumps excess current from the solar cells into heaters or load resistors on the cold side of the satellites. You have to maintain the temperature, right? To avoid overheating or uh, undercooling. Hmm. So for that you have different kind of uh, heaters and uh, other components to control the heat inside the satellite. Sensors on the batteries, power regulator, and solar cells monitor temperature, voltage, and current and supply this data to both the onboard control system and the controlling earth station via the telemetry downlink that we have discussed in a few slides back. Now, typical battery voltages are 20 to 50 volt with capacities of 20 to 100 meters ampere hours. 20 to 100 ampere hours. So these are the conventional uh, batteries.